Okay, let's say you have a circuit like this. Okay, there's a battery which is applying potential difference V across this resistor R. So if we call this delta V, we all know this is going to be V equals current through the resistor times the resistance. And this equation will be the paramount equation in these kind of problems. Potential difference across a resistor is equal to current times the resistance, right? Now, in order to find, let's say the question is, this is the circuit given to you, right? And you need to find a current. So if you know what what the potential difference is applied by the battery to find the current, you just do delta V over R, right? Now, things become more complicated when you have a more complicated circuit. So let's say you have a circuit like this. Let's say you have a circuit like this, where this is resistance R1, V1, let's say for fun we also have V2, yes, and one more resistor R2, and one more resistor R3. So look, this is the circuit, right? There are multiple batteries here, multiple resistors, and if you want to find out what is the current on this resistor, you can't directly solve this problem, can you? If you want to figure out, okay, this is the current at I2, you have no way of knowing that unless you know what is the potential difference across this resistance. Now this is where these rules given by a scientist named Kirchhoff, I guess, are applied and then are used. So if you use those rules, you can analyze these kind of circuits. You can figure out what is the current through a particular resistor, what is the potential difference across a particular resistor, and further down the road you will also try to calculate what is the power dissipated by a particular resistor. So all those kind of things can be figured out using the rules. So why do we need Kirchhoff rules? Why Kirchhoff's rules? General answer is to analyze the circuit, and that means to figure out currents in the circuit, and maybe power dissipated by a resistor in a circuit, resistor or resistors in a circuit, those kind of things. That's why we need Kirchhoff's law. And I have a habit of saying Kirchhoff laws instead of Kirchhoff rules, and in your book it is given as Kirchhoff rules. So it might happen that I'm saying Kirchhoff laws and instead of Kirchhoff rules, or sometimes Kirchhoff rules instead of Kirchhoff laws. Both are the same thing. So we have these. So Kirchhoff rules are used to figure out the current in different part of the circuits, and also power dissipated and some other things that you'll see in the future. Now we should see what these rules are. So Kirchhoff's, it's single O and double F apostrophe S rules, right? First rule is called junction rule, which says that at any junction summation of the current equals to 0. So at any junction or at any node, summation of all the current is equal to 0. Now we're going to see this in more detail in a while, but you should remember the junction rule is the rule that says summation of all the current at a node or at a junction is equal to 0. The second rule is loop rule. It says the sum of potential difference across all elements around any closed loop must be 0. This means in closed loop delta V equals to 0. Now these rules, for now, if you just remember them as given here, it will be beneficial. But further down the road, we'll see that these rules make sense because junction rule has to do with conservation of something, and then loop rule has to do with conservation of some other thing. So as promised, we're going to look at junction rule first, and junction rule is that in a junction, sum of the currents amounts to nothing. Okay, so let's say in a circuit, so what constitutes a junction, right? A junction is when you have, like, let's say this is, so it's easier to actually give you examples of junctions instead of try to explain it. So this is a junction, okay, this is a junction, this is not a junction, this is not a junction. So see, this little node, this is a junction, and this is a junction. So in a junction, if you add up all the currents, that will give you 0. Now if you have a junction like this, let's say this right here, right? So let's say this is current I1, this is current I2, this is current I3. The rule we follow when we write this equation, that is summation of I equal to 0, is whatever current is coming into that node or into the junction, we take it as positive, right? So it's going to be plus I1, and whatever current is leaving the node, we take it as minus. So we're going to do minus I2 minus I3 equals to 0. There you go. Plus I1 because that was coming into the junction, minus I2 and minus I3 because they were leaving the junction. Okay, an analog of this is, let's say if we have got two pipes coming in and they make a Y connection. Current, because current is a flow of charge, current is flow of charge, so we always that's why we are making this analog, a mechanical analog of three pipes coming together, joining at a point, and then they make a Y connection. So whatever flow rate is here, meaning whatever volume of water is coming in here per second, that should be equal to whatever volume of water is leaving here, and then whatever volume of water is leaving here, right? So whenever you look at a circuit and there is in a node there is some current coming in and there are some other currents going out, you should recall that there's a mechanical analog of this, and that is the amount of water per second coming in should be equal to the sum of the amount of water leaving in this case. So that's what junction rule is. And junction rule also has to do with conservation of charge. So as I said, these two rules, one they both are about conservation of something, right? So junction rule is conservation of charge. So whatever charge is being deposited per unit time in this node should be equal to the charge that is taken away from this node, right? That's how you think about junction rule. So this is a conservation of charge. It's the charge coming in is equal to the charge leaving out. right? So that's junction rule. Let's look at the second one. Second rule is loop rule. Just so that we can be on the same page with this, I'm going to read out this statement. It says the sum of potential difference. So like earlier when I was learning these things for the first time, I used to learn the definitions, because a lot of things in physics is, if you know what it means in words, you can write down the mathematics, and once you have written down the mathematics, it becomes just very easier to solve the question. So loop rule says the sum of potential difference across all elements around any closed loop must be 0. Okay, so I should really know how to calculate potential difference across anything. So let's say we have 4 examples. Okay, so I'm going to name the things in a minute, but you've got a resistor here, and then a current is going this way. Okay, you have some resistor here, the current is going this way, some battery like this, and there's another battery like this, and then this is positive and this is negative, and this is positive, this is negative. Let's say potential difference is epsilon. Okay, now using the black ink, so first of all, I'm going to demonstrate how to figure out potential difference across these elements. One is the resistor and the other is the battery. So let's call these two nodes, these two points, as A and B. Okay, and I need to find out this is defined as VB minus VA. Okay, and it's going to make more sense as we do the problem, and in the next video I'll try to solve a problem from your book, so that you can also cover your reading as you watch the video. So just think of this rule being an objective of calculating potential difference when you traverse an element. So what I mean by that is, let's say in a loop, there's a gigantic loop, and then there's a resistor R, right? And then you're coming in from left to right. So you see this black arrow tells you where you're coming in from. Okay, and we're going to make more sense, because loop rule has to do with a loop. So you go in a loop, and as you encounter different things, you write down the potential difference. What I mean by that is, let's say a very simple example: resistance R, potential difference V. So we go in a loop, right? So we start somewhere here, let's say C and then D. So this is what I'm doing. I'm coming in like this. Okay, and current also for the first case is here. So this is what I'm talking about. So you're in a loop, and you see you're coming in from the left and you're going to the right, and you see a resistor where in the direction of travel you have got current going in the same direction. Okay, so we have to figure out the potential difference, that is VB minus VA. Now remember, current always follows from, like this is how we think about it. Current always follow, and like basically current is the rate of flow of charge, right? So they always charge always follows the direction of the charge. The direction of the charge is always from a lower potential to a higher potential. Okay, so that means that because from a higher potential to a lower potential. I'm really butchering this, but this is what you should really hear. Charge flows from higher potential to lower potential. That means if I'm coming in from left to right, in the first case, potential at B will be smaller than potential at A, right? So I should get delta V equals to, remember this equation right here, IR is going to be true, but we're going to register this delta V as minus I times R. because potential at B is smaller than potential at A. Okay. Now let's say if you're coming in from right to left, and then you see that the current is in the direction, right? Then here, delta V, since it's B minus A, VB minus VA, because the current is flowing from B to point A, that means A is lower potential at B, so you just get the plus IR instead of minus IR, right? Similarly, if you start from here, like if you're coming from right to left and you see a battery, so delta V is going to be minus IR minus, I'm sorry, not IR, minus epsilon, because that is the potential difference across that battery, right? So because A has lower A has lower potential as B, see this minus and then this is plus. And if you're coming in from here, then delta V is going to be plus epsilon, because you're gaining this potential difference as you're crossing the battery. So if you remember these four cases and how we wrote down the potential difference, it will be very easier for us to understand and solve problems involving Kirchhoff's loop rule and Kirchhoff's junction rule. Junction rule is pretty easy, you just write down conservation of current. Loop rule is a little bit trickier, and as we solve more problems, we'll be able to understand more about it.